All right, welcome to section 5.7. We are talking about the fundamental theorem of algebra. And our essential question, how do the zeros help us write quadratic equations? And how can we apply the fundamental theorem of algebra to help us write those functions? So, we have a couple of theorems we're going to look at to start. The first is the complex conjugates theorem. And what that's saying is if you have a solution that is written in the form a plus bi, you would also have a minus bi as a solution. So the two examples here, if 2 minus I is a solution, then 2 plus I is also a solution. And if 3i is a solution, then negative 3i is also a solution. We're going to apply that same idea to the irrational conjugates theorem. So again, if one of your zeros can be written in the form a plus square root of b, then another solution is going to be a minus the square root of b. So like if 3 minus the square root of 5 is a solution, then 3 plus the square root of 5 is also a solution. So let's apply this to a few questions. And we're going to start off with the integer answers. But we are going to write a polynomial function for the given solutions x equals 2, x equals 4, and x equals 5. So recall when we talked about solutions, these are also known as the zeros of the function. They make x equal to 0. So in order to solve these, we want to get the right-hand side equal to 0 again. So we have x equals 2. So to make the right-hand side equal to 0, we subtract 2 from both sides. We can do the same with x equals 4. And then the same with x equals 5. And now you're going to take each of those 3 binomials and multiply them together. So x minus 2 times x minus 4 times x minus 5. Multiply your first 2 binomials together. And for that, if it's easier to just FOIL, you can first, outside, inside, last. So you should get x squared minus 4x minus 2x, and then plus 8, which is the same as x squared minus 6x plus 8. Then we're going to multiply our third binomial by the product of our first 2. So we're going to do x squared minus 6x plus 8 multiply by x minus 5, and then fill in each box by multiplying. And then you can combine your like terms. So for us, we have 2x squared terms, and we have 2x terms that we can combine. So when we write out our final answer, we should be getting x to the third minus 11x squared. Oops, that should be positive 30x. So we should be getting 38x and then minus 40. All right, let's look at another example. Again, we have 2 solutions, so we need to think about these as zeros. So you can either change the sign, or you can do like what I did on the last example. Subtract 3 from both sides. X minus 3 equals 0. For the other one, now we have imaginary numbers that we're looking at. So step 1, subtract 2 from both sides. We would like to square both sides to get rid of the imaginary number. And then one of our squaring a perfect square pattern, x squared plus 2ab or minus 2ab plus b squared. So this becomes minus 4x and then plus 4. And then when we take negative I squared, this one's kind of tough. This is kind of like negative 1 squared times I squared. I squared is equal to negative 1. Negative 1 squared is equal to 1. So this becomes negative 1. Add 1 to both sides. Then we have x squared minus 4x plus 5 equals 0. So now that we have two factors that are set equal to 0, we can go ahead and multiply this out again. And then combine our like terms. All right. We'll look at one more like that. So again, we already know these are solutions. Again, you can think about them as 0. So we need to have one side equal to 0. For the first one, subtract 5, x minus 5 equals 0. For our second solution, again, we have this, this x equals 3 minus square root of 2. So step 1, let's subtract 3 from both sides. Then we want to square the right-hand side and square the left-hand side. And again, when we square a binomial, this square of binomial pattern, the first term is x, so it becomes x squared. If we took x times negative 3, that's negative 3x, and then times 2 is negative 6x, and then negative 3 squared is 9. And then for this one, the negative square root of 2 squared is like negative 1 squared times the square root of 2 squared, which is the same as 1 times 2. Subtract 2 from both sides. And now we have two polynomials that we can multiply together. X squared minus 6x plus 7. Multiply that times x minus 5. Multiply all the terms. And then combine the like terms. X to the third minus 11x squared plus 37x minus 35. Okay, I am going to introduce the next topic. We are talking about Descartes' rule of signs. So if we have a polynomial function with real coefficients, the number of real positive real zeros of f is equal to the number of sign changes in the sign of the coefficients of f of x is less than this by an even number. So basically it means you're counting down by twos. The number of negative real zeros of f is equal to the number of sign changes of the coefficient of f of negative x, or less than this by an even number. So for example, if we have a function with degree 7, if f of x has 4 sign changes, then it could have 4 positive real zeros, or it could have, you need to count down by an even number or by twos. It could have 2 positive real zeros, or again, counting down by 2, it could also have 0 positive real zeros. And if we have f of negative x, and then it has 3 sign changes, we could have 3 negative real zeros, or, because again we're counting down by twos, we could have 1 negative 0. If we subtracted 2 again, we would be at negative 1, so we would have to stop. We can't go any further. It would either have to be 3 or 1 negative real zeros. Now if you come back up to the question, we have a degree 7 polynomial. That means we have a total of 7 zeros. Let's say that we do have 4 positive real zeros, and then we have 3 negative zeros. If there are a total of 7 zeros, that means there are no imaginary zeros. But what if we had 4 positive zeros and then 1 negative 0? Then that means we have 4 plus 1, that's 5 zeros. We still have a total of 7, so we would need 2 imaginary zeros. And let's fill in the rest of the table. Let's say we had 2 positive zeros. If we had 2 positive zeros and then say we had 3 negative zeros, we still need to have 7 total, but we only have 5. So that would give us 2 imaginary zeros. And then if we had 2 positive zeros, this time we'll say we only have 1 negative 0. 2 plus 1 is 3. We still need that total of 7, so there would be 4 imaginary zeros. And then if we had 0 positive real zeros, and then we had 3 negative real zeros, we still have a total of 7, so we would still have 4 imaginary zeros. And then if we had 0 positive real zeros, and then just 1 negative real zeros, that means the remaining 6 out of the 7 would have to be imaginary. All right, next I'll go over a couple examples for this type of question.